Tiende pamoja ndi mtima ummo. Tiende pamoja ndi mtima ummo.
Good afternoon, viewers. Welcome to the MTN Teleschool. My name's James Kabuye. I'm specialized in physics. And today we are going to revise together some physics questions from 2016, Pure Physics Paper 1. Okay, can you be with me? Now we read the questions. Question 1. Which of the following device can be used to measure the thickness of a 20 kwacha knot? That's the question about a 20 kwacha knot. So the possible answers are measuring tape, meter rule, micrometer screw gauge, and vernier calipers. Our task is to choose which one is the right one out of these. The issue is we must check on the convenience. That's number 1. Number 2, is this device appropriate? And number 3, is it accurate? And is it user-friendly? For now, we insist on accuracy. The accuracy of any instrument is such that it must give us such values that are very close to the value that we're looking for. For example, if the value we're looking for is 0 or 6.0 centimeters, and we have instruments, one instrument that can only give us no decimal place, the other instrument can give us 5.1 centimeters. The other instrument can give us 5.12 centimeters. The other instrument can give us 5.123 centimeters. Out of these instruments, the one that gives us more decimal places is said to be more accurate. In our case here, the micrometer screw gauge is the most accurate instrument and device out of these, so it becomes the right answer. We move on to question 2. The question reads, the diagram below shows a tube whose thickness is 3 millimeters. The first thing to do is to convert 3 millimeters to centimeters. So we are going to get 0.3 centimeters if we divide 3 millimeters by 10, because 10 millimeters will make 1 centimeter. After that, then we check the diagram that we are given so that we see how best we can make the reading out of there. So, allow me to draw this one just roughly very quickly before I explain everything on this one. I'll just draw some important issues here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If this value is for example 4, then we have 1, 2, 3, 4, 5. It means that one division is standing for 0.1 centimeters. One division is 0.1 centimeters. That means that we just look at the way this tube is held. The tube, if it's held here, and we draw it just roughly like this. When we draw it roughly like this, I'm drawing this as the thickness of the tube. So we have, I just want to depict what has been drawn on the diagram. So we have a set square here. Okay. right, let's do this. So we have a set square. All right, we have another set square here, just to make sure that everything is vertical. And so what is very important is to read the starting point and the end point. So our main issue is to see where it starts here and where it ends here. That is what is very important. So the reading now is here on the figure. It's showing 4, and at the end it's showing 7.4. So you can see that we are starting from 4 and ending at 7.4. That gives us the external diameter of this tube. When we subtract 7.4 minus 4.0, we are going to get 3.4 centimeters. This is the external diameter of our tube. The question says, what is the internal diameter of the tube? Just check what I'm drawing here. This is our internal diameter, which they are asking for. This is our internal diameter they are asking for. Therefore, we must take into account the thickness of this tube, which we had here as 0.3 centimeters. So the correct answer should be, therefore, 3.4 centimeters minus 0.3 centimeters, so that we get the actual internal diameter of the tube, which will be 3.1 centimeters. This is our right answer for this question. We move on to question 3. The question reads, the joule is a unit for measuring energy. Which of the following is equivalent to the joule? So you can see those possible answers. Newton per meter and Newton per meter square, and C and D. Now, how do we solve this problem? Let me clear this space so that you see how we are going to solve this problem. Fine. We must understand that a joule is a unit for energy, and work is done every time energy is expended. So therefore, work is related to energy. We must look out for work. Let's check. Work is equal to force times distance. Work is equal to force times distance. But force is equal to mass times acceleration. And mass is in kilograms. Acceleration is in meters per second squared. And D is in meters. Therefore, the unit for the joule should be equal to the work done. So therefore, we say work done is equal to F times D. Then we substitute what we put here, so that where F is, we put MA and we put D, and then we substitute now the figures that the units for M, which is kg, then acceleration in meters per second squared, and D is in meters. When we work on this, we find that the unit for joule is equivalent to kg meter square, meter times meter, and then s to the power minus 2. Because why? S to power 2 is at the bottom, and so when it comes on top, the power becomes negative. That becomes our answer. We move on to question 4. The question reads, a grasshopper jumps up with an initial velocity of 1.0 meters per second, reaching a height of 3.5 times 10 to the power minus 2 meters. Assuming that its deceleration is uniform, what would be the magnitude of the deceleration? That is the key word, deceleration. So when we look at this question and we write down the possible formulae that can be used to solve this problem, we quickly write them down and say S, which is distance, is equal to average velocity times t. Average velocity times t, where u is the initial velocity, v is final velocity, and divided by 2. The next one is v squared is equal to u squared plus 2as. Again, s is ut plus half of at squared. When we look at these equations, we also see v is equal to u plus at. When we look at these equations and then we notice that when we put down our information that is in the question, let's try and put it down here, data. We know that the initial velocity is 1.0 meters per second. Meters per second. U is 1.0 meters per second, and V we don't know, but S we know it is 0.035 meters. I've just converted that power to the decimals so that it's very easy for us to do. And then we also see that A, since this thing is jumping upwards, A will be equal to G, which we don't actually know this acceleration. How much of it we don't know. And so we can now look at these equations and see if 2 variables are missing, then we can't use that equation. If we check here, we find time is not there, and final velocity is not there, so we can't use this equation. When we check other equations, we notice that, in fact, other than that, the acceleration that they are looking for, which is deceleration, is not even there, so we can't use this equation. So let's check this one. We are looking for acceleration is there, and it's here. And S is given, U is given, final velocity is not given, so we can't use this one. If we inspect this one, yes, we can use it because we have the S, we have U, we have T, and we don't need the final velocity. So this one also we can't use it because the final velocity is missing. So let's use this one. When we use that equation, very quickly, S is ut plus half at squared. We must fit in very quickly the numbers that we have, the figures we have. So we have 0.035 is equal to, initial is 1. Okay, when we look at this also, we notice that we will have a problem also with it, because time is not given, and so t remains question mark. So we put x, and we see, what about if we say that, what about if we say that V squared is equal to U squared plus 2AS, and then we make A the subject, so we can say that, okay, in this particular case, each time it jumps up, it means that the final velocity will always be 0. Okay, so when it jumps up, final velocity is 0, so we say 0 squared is equal to 1.0 squared plus 2, and A we're looking for it, and S is 0.035. When we look at this very closely, we see that it's very helpful. So we transfer this to the other side, we see that it is negative 1.0 and equal to 0. If we multiply 2 by 0.035, we get 0.70, and I think that we get A. Okay, when we do that, what we can get is very quickly A becomes 1 divided by 0.07. When we do that, we get 14.28 to the nearest 14.3, which will be negative meters per second squared. Now, if we go back to the question, it says, what is the deceleration? When we look at the question, it says deceleration. It means that it has already a negative connotation in it. So we don't need this particular negative in the answer. Therefore, the deceleration becomes 14.3 meters per second squared. We move on to the next question. This was rather a good and challenging question, but I think that hopefully you have followed what we have done. If we move on to question 5, what we notice is that the motion of an object is represented by distance time graphs shown below. And then when we see that, we notice that the first graph is, we have distance, right? So we have distance in the y-axis, and we have time here. And when we look at the graph, it is going like this, horizontal. It means that the distance is not changing, and therefore that object is not moving. So that does not depict what we are asking for here, because they are saying that which graphs ABCD represents an object moving with a constant velocity. So the most important thing is constant. When constant is mentioned or uniform is mentioned, it simply means that it must generate a straight line. And therefore, this already eliminates B, which is curved up downwards, meaning that the velocity is reducing. The other one is curving upwards, which is D. It means that the velocity is increasing. So we are left with C, which shows a straight line, and that depicts a constant motion or uniform motion. Question 6. Question 6. When we check on question 6, it says that the diagram below shows a simple pendulum swinging between points A and C. So let's check what is happening here. It is swinging between points. So let's say that this is point A, B, and C. So it's swinging in this pattern like that. So they are saying that at what position or positions is the pendulum bob moving with maximum speed? Right, when we look at the question, let's look at what I'm drawing here very quickly. At position A, when it is released and begins to move towards B, going to C, we can say that at points A and C, this bulb is momentarily stopping. So therefore, it is not in motion. It has no kinetic energy. Maximum potential energy can be found here. Now, as soon as it starts coming downwards from C, its velocity starts increasing. As it passes B, the velocity reduces significantly until it becomes 0 when it reaches A, and the process repeats itself as it goes back to B. And so it means that basically as it passes B, it passes with maximum kinetic energy. So that is the point where it has maximum speed, at point B, because almost all the potential energy it had at point A has been converted to kinetic energy. And as soon as it passes B going to C, that kinetic energy begins to reduce and begins to be converted to potential energy until it momentarily stops at point C, where all kinetic energy will have been converted to potential energy. So, viewers, we have the maximum speed at point B and maximum kinetic energy. We move on to question 7. Hello viewers, we are on question 7. It reads, the vector diagrams below represent 4 forces acting at the same time and at the same point X as shown. Let's look at these diagrams very quickly together. The first one is showing this situation, point X, and the other one is showing this situation, 3 newtons, and here we have 4 newtons, and here we have 4 newtons, and here we have 3 newtons. All right, let me just write this properly. 4 newtons. Right, when we look at this particular question, how do we solve this problem now? These problems are solved better when you disconnect the forces and then reconnect them properly, you know, head to, you connect the tail to the head. That's the way we solve these problems. They are asking about the resultant force at point X. Resultant force means the net force that an object is going to feel as a result of the 2 forces pulling as shown in the diagram. So now, when we disconnect here, then we connect one force to the other, the tail of one force connecting to the head of the other force. So, let's try and do that. When we do that, what we have, okay, let me just rub this. Then we write this force. And now we have this other force that is going in this direction. We connect it here, and we represent it both in magnitude and direction. So you can see, viewers, that we have 3 newtons and 4 newtons. There's nothing we've done to it other than just connecting them properly. So the resultant force on point X is this one they are looking for, R. I'll represent it as R. How do we get it now? We use Pythagoras theorem and say that R squared is equal to 4 squared plus 3 squared. When we follow it up, we are going to get 16 plus 20, 16 plus 9, so that we get 25. Now, R squared is equal to 25. Therefore, R is the square root of 25, which means 5 newtons. That is the answer of the resultant force acting at point X. We move on, viewers, to the next question. Question 8. Question 8. All right, so the question reads, the diagram below shows a force of 20 newtons being used to pull an object of weight 50.0 newtons along a rough surface, resulting in a frictional force of 5.0 newtons. That is the question. So now the diagram has been drawn there. Let me just quickly draw it again for you viewers so that you see clearly what is happening here. We have this surface, and we have an object here, and it's being pulled by the force of 20 newtons in this direction, and we are told that the surface is rough, so it's resulting into frictional force of about 5.0 newtons. We must understand very quickly, viewers, that frictional forces, they tend to oppose the motion, and therefore this frictional force is going to be given a direction opposite to the first force. So we put here 5.0 newtons opposing the 20 Newton force. Now, this object, we are told it's a 50.0 newtons. We must deal with this problem first. We want the mass that is related to 50.0 newtons. Weight is equal to mg, where m is the mass and g is the acceleration due to gravity. This acceleration gives the mass some form of weight. So therefore, mass becomes equal to w, which is weight, over g, so that we say that therefore m is equal to 50.0 divided by approximately 10, so that we get 5 kgs. 5 kg, we put it here, that is the mass of the body. So the question says, what is the acceleration produced in the object? Okay, what is the acceleration? Now, the acceleration we are talking about is going to come about from the net force, from the resultant force. We must find the resultant force first, because that's the one that ends up giving us an acceleration. So basically, we must make sure that we find this net force. Okay, so how do we get the net force now? We say resultant force will be equal to 20 newtons, 20.0 for consistency, minus 5.0, so that we get 15.0 newtons. This is the resultant force acting on the body if we remove the frictional force. And this is the force, viewers, which is going to generate an acceleration on this body. Then we go back and say the actual force should be equal to mass times acceleration. We are looking for acceleration, therefore force over m, which means the net force is 15 divided by the mass. Okay, let me just move the page upwards. Okay, let me just rub. Right, there we are, viewers. We have the force of 15 newtons, and now the mass is 5, so acceleration becomes 3.0 meters per second squared. That becomes the answer. Question 9. Question 9. Question 9. The diagram below shows two forces of 40 newtons and 50 newtons applied to a spanner fitted to a nut. Viewers, I don't know if we'll try and draw this, but let me do this. Let me just draw a rough picture of what is happening here. So we have this spanner. Oh, never mind about the way I would draw it. Never mind. This is our spanner, hopefully. And it comes back like that. Okay, so that is our spanner. All right? So this is our central point. And so what happens now is that we have a force here of about 50 newtons. And then we also have another force here pointing downwards, 40 newtons. And then 40 newtons is about 30 centimeters from the turning point. This is our turning point. I hope you can see it, viewers. And then now we see the other force acting at 80 centimeters. I hope you'll be able to see this, you viewers. 80 centimeters from the pivot. Oh, sorry about that. Okay, I'll again put it back. Okay, 80 centimeters from the pivot. Fine. Now, they are saying that what is the turning effect of the spanner due to the two forces about C, the center of the nut? We must go for the net effect. So we have two moments here pulling in different directions. So one is a negative moment, the other one is a positive moment. So we must see the net moment acting on this spanner. So let's get these moments now. Moments can be found by saying force times distance. Force times the perpendicular distance that that particular force is acting from the turning point. So moment one, the first moment is, let's take 50 newtons. We say 50 newtons times 80 centimeters. That's one moment. The other moment, let me just write this properly. Moment. All right. Moment one, I'll call it moment one. Then we have moment two, which is 40 newtons times 30 centimeters. So the unit will be Newton centimeter, in both cases. So the first case gives us, for example, the first one we say 50 times 80. So we get, okay, like here we get 400 Newton centimeter for this one. Okay, and then once we do that, very quickly, let me remove this one so that you don't get confused. The next one is moment two, which will be 40 times 30, giving us 1,200 Newton centimeter. The difference between the two gives us the net moment. So 4,000 minus 1,2, it will give us 2,800 Newton centimeter. That becomes the answer. We move on to question 10. A motor is used to pull a 10 kg mass box along a 5 meter long incline as shown in the diagram, and the diagram is shown there. Very quickly, we look at what is happening, ignoring all frictional forces, determining the work done in pulling the box from the foot of the incline to the top of the incline itself. So very quickly, what we do is that, okay, viewers, sorry about this, we have to go for a short break so that we relax a little bit and then we'll proceed from there. Just for a short while. Thank you so much for being with us.
I told the bus driver that I work hard for my money, so it better gets to Chipata.
Yeah, that's right. That's what I told him.
Yeah.
Weather, drama nizingono, or nizambili.
Tituma. And he kept trying to tell us something, but I was like, Ukagamba, Tilo.
Cause cash money yeve across Zambia.
Tituma. At bus and Kuchpat. The end of South Africa. Hello, what?
Run, K-Star, run! You don't got the
Sending money doesn't have to be this dramatic. Open an MTN mobile money account today and send money to friends and loved ones across Zambia instantly. Dial *303# to send money with MTN, Zambia's #1 network. With MTN mobile money, Tituma.
MTN, everywhere you go.
Rise up this morning, smile with the rising sun. 3 little birds pitch by my doorstep, singing sweet songs, our melodies pure and true, saying, this is my message to you. Singing, don't worry about a thing, 'cause every little thing is gonna be alright. Singing, don't worry about a thing, 'cause every little thing is gonna be alright. Cause every little thing is gonna be alright.
How you use your data is up to you. With the widest network coverage, it's amazing what you can do on MTN.
This is my message to you.
Welcome back, viewers. Thank you so much, Mr. Chimpusa and Mukuka. We appreciate. And Edward, Hilda, Morris, and Benjamin. Marvis, thank you so much that you're watching this program, and I hope that we can run through together again. We move on to question. We were almost doing question 10. Okay. So question 10, viewers, we have an inclined plane. I'm going to just do it roughly very quickly. And we have a body that is going upwards, and it's going to go through 5 meters. And this is the box. And then it is, there's a motor here which is pulling it, and it has gone 4 meters. Right, so the question says, ignoring all frictional forces, determine the work done in pulling the box from the foot of the incline to the top of the incline. You must understand, viewers, very clearly that work can only be done against certain forces. When you don't do work against certain forces, then there is almost no work done. So you can see that we are ignoring all the frictional forces that are existing on this inclined plane. So we want to see how much work is basically done in bringing up this object to the top of that particular height. So the work done will be equivalent to the gain in gravitational potential energy when this body reaches the topmost point where it's going. So when we look around for the work that has been done, basically we'll be able to find it in the gain of in terms of gravitational potential energy of the body as it reaches the top here. I'm talking about here. As soon as it reaches here, we can find the gravitational potential energy gained. Now, this potential energy will be equal to mgh, so that we say mass is actually 10 kg, gravity is 10, the height is 4. So we get 400 joules. That is the gain in gravitational potential energy. And this tells us that this is the work that has been done in moving this object above the inclined plane. Question 11. A man lifts a load of 1800 newtons using an effort of 400 newtons. If the pulley system is 80% efficient, determine the velocity ratio of the system. Viewers, let's solve this problem very quickly together and see. Let me create space here very quickly so that we solve this problem together. Let's see now here. Efficiency represented by a letter indicated here, efficiency, will always be equal. This letter is called eta. Eta is the symbol for efficiency. And so we are going to say that a mechanical advantage over velocity ratio times 100%. This is going to give us the solution to the problems that we're going through. Now, mechanical advantage on its own is the load over the effort. Load over effort. Very quickly, what we see is that the load is 1800, the effort is 400, therefore mechanical advantage gives us 4.5. So we can now say that efficiency, which is 80%, is equal to 4.5 divided by velocity ratio times 100. When we say that 80 times velocity ratio will be equal to 4.5 times 100, then velocity ratio becomes 4.5 times 100 divided by 80. When we do all this, what we notice basically is 45 divided by 8, which gives us approximately 5.6. That is the velocity ratio. Thank you so much. That's the velocity ratio. Question 12. A rectangular metal bar exerts a pressure of 15,200 newtons per square meter on a horizontal surface on which it rests. If the height of the metal bar is 80 centimeters, what is the density of the metal? Very quickly, let's sort out this matter now. Okay, so the pressure is 15,200 newtons per square meter. This is the pressure. We must, the question says, if the height of the metal bar is 80 centimeters, what is the density of the metal? Density is mass per unit volume of a substance. So, we must find the volume. We convert this to volume, we must convert this to mass. When we do that, what will happen is that we say, if this is the weight, then just allow me to remove this and say weight is equal to mg, which means m is equal to the weight over g. That means that 15,200 divided by 10 gives us the mass, which will be 1520 okay, 1520 kgs. That is the mass. So we quickly bring it here, and then also we get the volume. We are told that the height is 80 centimeters, so we must multiply by that meter, so that we say, okay, in that case then it means that the density will be equal to mass over volume, so that the mass is 15,000. No. I beg your pardon. 1520 kgs divided by 1 meter square times 0.80 meters. So, when we do all this correctly, we'll find that this gives us the volume in meter cubes, and this gives us the mass, so that will give us the density. So when we divide properly, we'll get 1,900 kgs per meter cubed. That becomes our answer. Question 13. A fixed volume of a gas is collected in a cylinder. Energy is removed from the gas. What happens to the pressure and the temperature of the gas in the cylinder? We can only solve this problem, viewers, when we think about the kinetic theory of matter. It indicates that matter is made up of particles that are in a continuous state of random motion. So they are colliding amongst themselves, they are colliding with the walls of the container, and these collisions, these movements are directly proportional to the energy. The more the energy, the more the collisions, and the greater the forces that they hit the surfaces with as they move around in that particular container, in this case a cylinder. So, since the movements are direct proportion to the energy, the removal of energy means that the particles move slower, at a slower pace, lower velocities, and so the pressure reduces, and the temperature also reduces, because the temperature is proportional to the energy that the particles will have. So the correct answer is the pressure reduces and temperature also decreases. Question 14. Which of the following statements best describes the specific heat capacity of a substance? When the word specific is mentioned, it means that they're looking for a unit mass of a substance. But when they just say heat capacity, they're just talking about how much energy is required to raise the temperature of a substance by 1 degree C. But when they say specific heat capacity, they are referring to the unit mass. So in this particular case, we are looking for the heat that is required to change the temperature of a unit mass of a substance by 1 degree C. Not changing the state. Changing the state requires latent heat. So the right answer becomes C. Question 15. A learner observes smoke under a microscope and observes a bright point moving randomly as represented in the diagram below. So you can see that diagram, viewers, in the question. The bright spot moving in a zigzag fashion is, obviously we cannot see air molecules because they are very small, so it simply means that the bright points could be the specks of smoke. These are the only things that we can see hitting against the invisible air molecules and also hitting amongst themselves. Question 16. The diagram below shows a vacuum flask. Dear viewers, when you look at this vacuum flask, there is a part that has been magnified there. We must look at those points that have been labeled Y. The other ones are labeled X. I hope you are able to see those points which are shown there. They are saying which processes of heat transfer do parts X and Y affect. So we must quickly realize that Y is actually a vacuum and X are silvery painted surfaces. The vacuum means that there is neither solid nor gas present there. So it means that there is going to be a reduction in heat transfer in terms of conduction and convection. Because without particles, there can't be convection. Without particles, then conduction cannot take place. So that part is preventing heat transfer through conduction and convection. That is part Y. Then part X, the silvery painted surfaces. They are reflecting back the energy that should have otherwise passed through the vacuum, because through radiation, heat passes through the vacuum. So it's going to be reflected back by those silvery painted surfaces. So the correct answer becomes X, preventing heat transfer via radiation, while Y is preventing through two processes of conduction and convection, because there is neither a solid nor gas in that space. Question 17. A liquid in glass thermometer contains mercury. Which physical property below varies with temperature? In this particular case, we're looking at volume. The volume of the liquid is going to be obviously changing as the liquid expands with the absorption of energy. So the right answer becomes volume, which is this. Fairly straightforward, viewers, this particular question. Question 18. A VHF radio station broadcasts at a frequency of 100 megahertz. Let's look at this question very clearly, viewers, as we analyze it. We must have a problem with 100 megahertz. we must take it to hertz, because hertz is the correct unit for frequency. So, just allow me to wrap this. When I do that, then I go back and write something to say mega means 10 to power 6. So that means that this should be 100 times 10 to the power 6 hertz. Okay? In that case, we can also say that this is 1.0 times 10 to the power 8 hertz. Okay, that has been resolved. So we go to the question, what is the wavelength of the wave broadcast by the station? One piece of information is missing again in this particular thing, but the concept behind is that we must understand the properties that are common to all electromagnetic waves. We must understand that all electromagnetic waves move at a particular speed in a vacuum. If not in a vacuum, this speed is very similar to the speed that they travel at, even in air. That speed is 3.0 times 10 to the power 8 meters per second. That is the speed of all electromagnetic waves. So that speed has not been given here because they think that we must know, because that is one property we must be aware of all electromagnetic waves. So let's have the solution now. The equation says velocity is equal to frequency times lambda, where v is velocity, which is the speed, and f is the frequency, and lambda is the wavelength of that particular wave. Now, what can we do now? We are looking for the wavelength. So we make lambda the subject, so we get velocity over frequency, so that we say velocity is 3.0 times 10 to the power 8 divided by frequency, which we found there, 1.0 times 10 to the power 8. So, having done this, we can comfortably cancel out these powers so that we remain with 3.0 meters as the wavelength of these waves. We move on to question 19. The diagram below represents a longitudinal wave traveling to the right. Okay, so viewers, what we see are a series of compressions and rarefactions in that particular longitudinal wave. So let's just quickly draw them roughly here. I'll just draw them just roughly. Never mind. Just roughly. I want to stress one point here, that these lines that you see here, they represent what are called wavefronts. And a wavefront is a line in an advancing wave which represents particles that are oscillating in a particular pattern. Similar pattern. If what I'm saying is that this line represents particles that are vibrating in a similar pattern. It means that the pattern for this way is the same as this. The pattern for this is the same as this. Okay? And the pattern for this is the same as this. The pattern for this is the same as this, and so on. So you can see that the distance from one pattern to the next similar pattern gives us the wavelength. So if we get this one, then we must come as far as here. If we get the middle one, then we must come as far as the middle. So let's check now how far this is. We know that from here to here, it will be 14 meters. So that becomes our wavelength. Same from here up to here, and from here up to there. It's the same thing. So what we will say is that the frequency of the wave given above is already given, which is 24 hertz. So the speed therefore becomes frequency times wavelength, which means 24 times 14. This will give us 336 meters per second as our answer to that question. Okay, we move on to question 20. The question reads, Elena stands 80 meters. Please allow me to be drafting what is happening now very quickly. So Elena stands 80 meters from a high wall. Let's say this is the high wall. So Elena stands 80 meters. This is the learner. Okay, so stands 80 meters from this wall. Okay, let me do it properly. The learner will be here. Okay, 80 meters from there. This is our tall wall, high wall. And claps 2 planks in such a way that each clap made is synchronized with the echo of the previous clap. The pupil makes 9 claps in a time of 3.6 seconds. Determine the speed of sound on that day. So what we do very quickly is to see that we must understand what an echo is. It's the reflected sound. It goes and comes back. So viewers, this sound produced here goes and comes back here, meaning that it is covering twice the distance that